Hello, everyone. My name is Jatin Arora. I'm a PhD student at Carnegie Mellon University, advised by Umut Acar. And today I'm going to be talking about managing memory for parallel functional programs. This is joint work with Sam Westrick and my advisor. So, parallel hardware is everywhere. We have personal devices with 10 cores to workstations that have up to 100 cores on a single chip, and even monsters like the machine, which has thousands of cores in total. But it's extremely challenging to code software for it. There are two key issues, correctness and performance. So, correctness is challenging because you generally have to worry about deadlocks, live locks, race conditions, non determinism, and whatnot. Performance is challenging because there are a lot of low level optimizations that are needed for performance gains. It requires deep understanding and expertise of the hardware to make your code scale really well. So, coding software to take advantage of these machines takes years of work. Many procedural languages have been proposed for parallelism, but they are not working out. The issue is that these languages are difficult to write parallel codes correctly in. With little to no control over effects, their programs are plagued with data races that lead to very insidious bugs. Their programs are also difficult to read and debug. Fundamentally, the issue is that parallelism causes an explosion in the state space, which makes it very difficult for the programmer to reason about the correctness of their code. Researchers have therefore proposed functional languages. The key benefit of functional languages is that pure functional programs are parallel by default, and it's easier to reason about their correctness. You can understand the code and read the code and reason about the code without thinking about how it executes in parallel. They provide higher order features, which operate over collections of data. And if you use bulk operations like map, filter, reduce, there's a natural opportunity for parallelism. Most of these languages also come with powerful type systems that offer strict control over effects and mutation. And this control allows the programmer to prevent race conditions in their code. And there's been a lot of pioneering work in this context. Multilisp was developed in the 80s. Irwin's id was even before it. Blalock's Nestle was in the 90s. And these languages have influenced a lot of ideas in parallel Haskell, Manticore, Futhark, OCaml, Multimilton, several other forms of parallel ML, and various other languages. Despite all of this work, we don't know any functional language that can compete with well-optimized procedural programs. The elephant in the room is, can parallel functional programming compete with the fastest techniques? This difference in efficiency is not because of compilers. Modern compilers are very good at optimizing all kinds of code. The fundamental problem is that functional programs allocate orders of magnitude faster, which slows down execution because memory is the bottleneck. Parallelism only aggravates this issue. While you can do p additions in parallel, you can't allocate p times faster. Good memory management is thus crucial for efficiency because of these high allocation rates of functional programs. Memory management for sequential functional languages is essentially solved. We have many work and space efficient algorithms and numerous implementations that can compete with really low level procedural code. However, on the parallel side, provable bounds are rare. I know of only one bound, and that was by Blalock Cheng from 2001. It was primarily meant for real time systems. Proving bounds for garbage collection is tricky in this context because if you run a program on P processors, you may need P times as much space. Another challenge in proving bounds is that different parallel runs can have arbitrarily different space usage. So there's nothing to relate to. This problem isn't just theoretical. Efficient implementations are also hard to come by. So uh, memory management in parallel functional languages is very much an open problem. And if we can solve this problem, it will enable the everyday programmer to access all that hardware elegantly. So in this work, we present new techniques for memory management that A, can cope with the high allocation rates of functional languages, and B, guarantee work in space bounds. The key, so We do all of this by using disentanglement. Disentanglement is the property that concurrently executing threads do not access each other's data. So if a thread is concurrently executing with another, then this thread is not allowed to see or read whatever the other thread is allocated. So this allows us to structure memory in a whole new way. The key idea then is to combine thread scheduling and garbage collection. So just like a thread scheduler schedules threads among processors, we have a heap scheduler that schedules memory among processors. What we essentially do is we partition the memory into thread local heaps and assign these heaps to processors. We also show work and space bounds for our techniques. We do this by relating the space usage in parallel executions to a sequential execution. I'll tell you more about it when I come to the bounds. Before I go into the details, I want to tell you how our implementation competes with Go and Java. So we have implemented all of our techniques in Maple, and we conducted a sorting competition. We obtained highly optimized parallel implementations of sorting in Go and Java, different algorithms. And we implemented a merge sort of our own in Maple, which is our compiler. So if you look at the speed up curves on the left, our plot in blue scales linearly up to 70 cores. Note that higher is better in this plot. Now, if you look at the table on the right, all of these numbers are within factor 2 of one another. On single core times, T1, Java is the fastest at 139. And on multi-core time, which is T70, 70 cores, our implementation is faster by a wide margin at 4 seconds. Now, if you take a look at the space numbers, R1 and R70, Maple and Java use approximately similar space. They have similar performance. Go uses half as much space. That's interestingly, but it is also the slowest on one core. The takeaway here is that it is feasible for parallel functional programming to compete with state-of-the-art parallel systems. I will show other interesting results, but those come towards the end of the talk. So now I'll tell you about some of the details of our work. So we consider those programs that are written using the fork join primitives. You can think about these programs in terms of tasks. So imagine writing a divide and conquer algorithm where you fork two subtasks to compute them in parallel. So these subtasks may fork other subtasks. And then you join back the results of the subproblems to produce the final result. Like Opera, our runtime gives each task its own heap. The idea is that each task uses its heap to allocate objects into. This allows us to ascribe each object to a task. So we can answer the question given an object, which task allocated it. On a fork, we create two new empty heaps for the children tasks to use. And at a join, we merge these heaps back with the parent. So at any point in the computation, we have a heap tree and a task tree. And I have superposed both of them to show the one-to-one correspondence. In this tree, the internal heaps and tasks are suspended, while these leaves are executing in parallel. So these leaves are executing in parallel on different processors. They are allocating objects, they are manipulating data, they're doing all sorts of stuff. Each of these leaves is a functional program in its own right. So each of these leaves is allocating at a very high rate parallelly. And in order to keep up with these leaves, we need to divide the memory management work among processors. So in our runtime, we use a heap scheduler to do it. So we schedule each heap on a processor, just like you schedule threads on processors. So what our heap scheduler essentially does is it takes the heap tree and partitions it into bubbles. Then it assigns each bubble to a processor. The idea is that each processor does memory management within its own bubble. And these assignments of bubbles, these bubble assignments are made in tandem with the thread scheduler. So I'll show you how this works with an example. There's a lot going on here, and I don't want to go into too many details. So if you get confused, just count the number of bubbles at each step. So the program starts at the root task. It has a root heap, and there is just one bubble. When the program forks, the thread scheduler will create another thread for it. So the heap scheduler will follow suit and create another bubble. just like a thread scheduler created a thread. At another fork, the thread scheduler will create yet another thread, and the heap scheduler will create yet another bubble. So, so the heap scheduler creates bubble as the program forks. At a join, a thread will merge with its sibling thread. So the heap scheduler will merge the bubble with its siblings bubble. And this is the idea. The idea is that we fork and join these heap regions just like we fork and join threads. The takeaway from this slide is that we are scheduling the memory just like we schedule threads. And each processor manages the memory that is scheduled on it. We show bounds with heap scheduling. Specifically, we show that executing a race-free program on P processors requires at most R star times P space and W plus R star times P work asymptotically. Here, W and R star are the sequential work in space. So if you look at the space bound, there is a R star times P, right? So this P blow up is expected because if you use R star amount of space in sequential execution, then there are programs that will allocate P times that if you execute them in parallel. Basically, each thread is allocating the same amount of memory as it would have in sequential. The proof of the space bound, the key idea behind this space bound is simple. So what we do is we compare the memory in each bubble to the memory in a sequential execution. So this is where we use the race-free assumption. So if the program is race-free, then the sequential execution and parallel execution are similar enough in order to compare their space usages. So essentially, we prove that each bubble requires at most R star amount of memory. And because there are P bubbles, the total amount of memory is bounded by R star times P. The work proof is similar. There are a lot of details here, but there is a R star times P extra factor in the work bound. So this factor is a consequence of how we distribute the heaps among processors. So what might happen is the same heap might end up getting collected after joins because it shifts bubbles. And we bound that this happens only P times. This factor may be a consequence of our proof technique because when we do our evaluation, we don't see it come up. I'll talk more about it when I discuss the evaluation section in detail. So race-free programs satisfy a nice memory property called disentanglement. Let me tell you more about disentanglement. So disentanglement is a property on the memory graph of a program. It states that looking at an object and looking at which heap it resides in, an object can either point up or down or internally, but not across. So it restricts the object to only refer to objects in the root to leaf path of its heap. It essentially forbids cross pointers in the hierarchy. Actually, this entanglement is very general. It holds for programs that use no mutation, that are pure. It holds for programs that use mutation but do so in a race-free way. And it even holds for programs that use mutation in a racy way, but are structured in the sense that concurrently executing threads are unaware of each other's allocations. Okay, so why am I telling you about disentanglement? This is to say that even though our bounds only work for race-free programs, our techniques are applicable more generally to all disentangled programs. And I'll show you how. Now let's get back to our bubbles. So we use disentanglement for collecting bubbles independently. There are a lot of low-level details, so I will only talk about the interesting bits. To collect a bubble, we need to determine the pointers that come into it. Because of disentanglement, we only need to worry about up pointers and down pointers. Now, if you look at the highlighted bubble, the up pointers into it are from the child that is not in the same bubble. The way we handle these is preparing by these pointers ahead of time. So at the time of fork, we would have copied the closure of that child and stored it. Everything that is reachable from that child's heap is reachable from that closure. So this closure is essentially a summary of up pointers from that heap. To remember down pointers, to handle down pointers, we use a write barrier. Each time a down pointer is created, we store it into a remembered set. So now with the remembered set, the closures and the program locations, we have all the pointers into the bubble and we just have to go and collect it. So I'll show you how we collect each heap in the heap tree. As an optimization, we use two different collection algorithms for collecting heaps. So we divide the hierarchy into two parts, public and private. The heaps above the yellow jagged line are public. If you look closely at a public heap, you'll see that its children are in different bubbles. Therefore, because different bubbles are assigned to different processors, the data in that shared heap, the data in a public heap is accessible by multiple processors simultaneously. So we need to be more careful when we are collecting these heaps. We use a concurrent non-moving algorithm for collecting public heaps. And these are the heaps for which the heap closures and remembered sets are used primarily. The heaps below the yellow line are private. No other processors access their data. So we can use a Cheney style moving algorithm because it is generally better for locality and fragmentation. This is merely an optimization because that is done for fragmentation reasons. So this separation between public and private is dynamic. It changes as the computation evolves. The same heap could be private to begin with and then turn public after a fork because its children are now in different bubbles. We have implemented all of our techniques in the Maple compiler. So Maple is a compiler for parallel ML, which extends Milton with fork join parallelism. We have integrated work stealing and heap scheduling. We have implemented snapshotting, remembered sets, private and public collectors, everything that I just described. We have some benchmarks that come from a wide variety of problem domains, and we compare it against Milton. So Milton is a very fast and established compiler for sequential ML. It generates very good code. So it is a good sequential baseline for us to compare our techniques against because we are talking within the same language. So the overhead column here shows how much extra time it takes Maple to run the same benchmark on one core with respect to Milton. So mostly these overheads are around 30%. These overheads are due to the differences in the underlying compilers. The speedup column shows how much faster it is to run on 70 cores with Maple as compared to Milton time. We get nice speedups ranging from 12 to 51x. These speedups vary because some benchmarks like SeamCarve is third from the bottom, are compute bound. So SeamCarve is a compute bound benchmark. SeamCarve is a memory bound benchmark. So throwing more CPUs at it doesn't speed it up. So it shows a relatively less speed up of 12, whereas other benchmarks like Ray and Random show good speed ups of around 37 to 51. The point to take away is that if you were to carefully implement and optimize these benchmarks in parallel for C or C++, you would see similar speedups. This is a similar table, but for space. The first column shows how much space Milton requires to run these benchmarks. So you can think about this as an approximation of R star, the sequential baseline in the proof bound, in our space bound. The blow up on 70 cores is the ratio of Maple space to Milton space. Recall that we proved that if it requires R star amount of space to execute a program sequentially, then our upper bounds the space usage in parallel execution by R star times P. So what essentially in this context, these bounds mean that the blow up will be less than 70. So we see mostly that in the blow up column, these blow ups are less than 5 on 70 cores. SeamCarve sees a blow up of 36 because it has a high allocation rate. It is memory bound, like I mentioned before. But still it is less than 70, so it is within our theoretical bounds. Technically speaking, what's difficult about the bounds and the implementation in our work is the collection of public heaps. So these are the heaps for which the overhead in terms of snapshotting and heap scheduling really factor in. So what we did is to show the effect of public collections to get the effect of public collection on performance, we ran Maple with public collector turned on and public collector turned off, just to measure the impact of, just to measure the overhead from public collections. So if you look at the time difference, the numbers are pretty small. So this time shows the difference between these time shows how much time it takes with the public collector, how much extra time it takes with the public collector. So if you look at this difference, the max difference is 25%. But generally, these differences are less than 10. This means that the practical overhead of public collections is actually low. And this is what suggests that this R star times speed term in our work bound maybe lacks. At least it doesn't show up for these benchmarks. However, with the public collections turned on, we see big improvements in space. Benchmarks towards the bottom of the table, like seam carve, reverb, suffix array, see improvements in the range of 70%. And as I mentioned before, these are very memory intensive benchmarks. So these percentages are good numbers in absolute terms also. Anyway, the takeaway here is that the time overhead is low, but the space gains are huge. Let me summarize. By this idea of a heap scheduler, we show a way to integrate memory management and thread scheduling. We show provable bounds for race-free programs and show that it is feasible for parallel functional programming to compete with procedural code. A natural question is, can we extend heap scheduling to entangled programs? So right now, we only know how to collect bubbles if the heap hierarchy is disentangled. We are curious to see if we can extend the collection to entangled bubbles. The bounds are also tricky for entangled programs because these programs tend to be very racy, and it is difficult to compare them to a sequential run as we did in this work. In this paper, we considered fork join parallelism. While it is a good fit for a variety of applications, there are other applications that may benefit from more expressive models of computation. For example, interactive applications are very difficult to express with fork join. So we are interested in extending and understanding disentanglement for other models of parallelism, like futures. And then if we extend disentanglement, maybe we can extend these techniques to those models. Currently, our compiler assumes that the input program is disentangled. So it does unexpected things when the program is not disentangled. So we want to develop a checker for disentanglement, so we can warn the programmer that, okay, you have to fix this. So one way to check for disentanglement is to check for race freedom, because recall that race freedom implies disentanglement. So if the program is race free, then it is disentangled. But that's a restriction because disentanglement is actually more general. In particular, we have seen several parallel graph algorithms where races are used for efficiency, but the program itself remains disentangled. So we want to build a dynamic checker that checks for entanglement. That's all I have to say. Thank you very much for listening to the talk. I'm happy to meet anytime for more discussions.